Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 14.1, day 2, entitled Counting. And in the previous section of notes, we talked about the fundamental counting principle and then permutations. So today we're going to talk about combinations, which we've kind of already seen, and then how to know the difference between permutations and combinations, or when to use both of them together. Okay, so when we're dealing with combinations, this is when an order does not matter. So that means that if you have AB and BA, they're the exact same thing. It doesn't matter if A comes first or if B comes first, as long as A and B are together. That counts as one combination. Okay, so here it says a combination of R elements of a set is any subset of R elements from the set without regard to order. And if the set has n elements, then the number of combinations of R elements is going to be denoted as C and R. So the C again means we're going to use a combination. So this is called the combination of n elements taken R at a time. And down here they have a brief example. It says that we're going to consider the set of 4 elements, A, B, C, and D, and the combinations of those 4 elements taken 3 at a time are going to be listed below. So we could start with A, and then we'd have BC or CD right here. And then we could also have ABD. Instead of ABC, we could have ABD. Okay, but notice that they're not listing ACB. So if we wanted to list them all out, like we had before, if our first choice was A, my second choice could be B, and then I could have C. Or if I did A, B, D, that would be an option. And then I could still start with A, and I could have C as my second one, and then B, and then A, C, D. But notice that ACB and ABC, they're the same. So I'm not going to count this one because it's already been counted here with the ABC. So this is what they mean by order not mattering, okay? As long as you have 3 that are grouped together, then that's just considered one combination. Okay. So we notice that the number of combinations is a lot fewer than the number of permutations, and that's because you're getting rid of any repetition. Okay. So basically, we're going to take our permutation that we would have gotten for 4 elements 3 at a time, and then we're going to divide it by those repetitions. So we're going to have our formula down here at the bottom. So for a combination, we're going to have n factorial over n minus r factorial, just like we had for the permutation, but then we're also going to divide it by r factorial. Okay, now remember that the key difference between permutations and combinations is order. Okay, when you're dealing with ordered arrangements, that's a permutation. So order matters for permutations. If we're just counting without regard to order, then that's a combination. So I kind of like to remember P and O, permutations and order. For permutations, order matters. So you can kind of remember Poe, like Edgar Allan Poe, or come up with some other type of little funny thing like that, some mnemonic device to help you remember it. Now we're going to do the example 7 next. But here what they're referring to is example 5, and that was what we did in the previous section of notes. So if you want to look back to that where order does not matter, you can, but for example 7 coming up, oh, I'm sorry, I said that wrong. If you want to look at example 5 where order does matter because it was a permutation, you can compare that to what we're going to do next in example 7 where order doesn't matter. Okay, so here a club has 9 members. And how many ways can a committee of 3 be chosen from the members? Now, when we saw this in example 5, it actually listed the exact positions that they wanted: president, vice president, and secretary. So when you have a specific position that you're trying to fill, that's a little clue that order matters there. But here they just want a group of 3. So if you pick Sally and Bob and Joe to be in a committee, that's the same as picking Joe and then Bob and then Sally. All 3 of the same people are together. So this one, order doesn't matter. So this is going to be a combination. So we're going to have 9 committee members, and we're going to combine them into groups of 3, 3 at a time. So again, you can do this on your calculator if you go to the math menu and then arrow over to probability. I think the combination is option 3 on the menu. But what the calculator is doing is it's taking 9 factorial over 3 factorial times 9 minus 3 factorial. And again, the 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then the 3 factorial will be 3 times 2 times 1. And then 9 minus 3, that's 6. So that's 6, 5, 4, 3, 2, 1. So previously, when we were doing this problem with a permutation, we just crossed off the 6, 5, 4, 3, 2, 1 from both of them. But now this 3 times 2 times 1, when we divide by that, that gets rid of all the repetition. So that, if you already have ABC, that gets rid of CBA. Okay? And you can do some canceling here if you'd like. If you want to cancel the 3 into the 9, you can. If you want to cancel the 2 into the 8, you can. So then you're just doing 3 times 4 times 7, and you should end up with 84. So now there's only 84 ways to combine a group of 3 members, or to make a group of 3 members out of 9 total people. And previously we had way more than that. So combinations, remember, you're going to get a lot smaller number, and that's because we're getting rid of that repetition. Now, we're not just going to take a look at simple permutations and combinations all the time. We're going to see some problems where both of them are involved. So a crucial step in solving counting problems is deciding when to use permutations or combinations or the fundamental counting principle. Remember, that's just where we multiply like the number of options for each event. And in some cases, the solution of a problem may require using more than one of these. So your book does have a pretty helpful tip here, a little guideline. You want to ask yourself first if you have to use the fundamental counting principle. So when consecutive choices are being made, use the fundamental counting principle. And then if that's not the situation, then you ask yourself, does order matter? And if order does matter, then we use permutations. If order doesn't matter, then we use a combination. Okay? So our last example then is right here, example 10. We have a committee of 7 consisting of a chairman, a vice chairman, a secretary, and 4 other members. And it has to be chosen from a class of 20 students. So now when you're reading this, hopefully you notice that there's actual positions that they're trying to fill. There's a chairman and a vice chairman, the vice chairman here, the secretary. So there's 3 positions where order matters, because the people or the person who's serving as chairman and then somebody else who's serving as vice chairman would be completely different if their roles were reversed. So order matters for the chairman, the vice chairman, and the secretary, but those 4 other members, they're just kind of an afterthought. It says, and 4 other members. So that means there's 4 where order doesn't matter. So I'll just say no order here. So basically, this is a combination of permutations and combinations. We're going to use both of them. So what we're going to have to do then is we're going to find our total. So for those 3 where order matters, we're going to have to do a permutation. So we have 20 altogether, 20 students altogether that we're choosing from, but we only want to choose 3 of them. So if you do that in your calculator, you should get 6,840. And then the ones where order doesn't matter, that's going to be a combination. And again, we have to think that those three members for the chairman, the vice chairman, and the secretary are going to be chosen first. So after those three people are selected, we really only have 17 people left to choose from. So that's kind of another thought process that we have to be aware of and we have to take into consideration. So when we're choosing those four other members, we're going to choose them out of the 17 that are left over. So we're going to have 17 combination 4. Okay, and when we do that on our calculator, we're going to have 2,380. Okay, so now to find our total, we have to consider how many options there were for the first choice. Okay, so that's where order mattered. That was our first choice. And then we'll have to consider how many options there are for our second choice. So that was where the order didn't matter for the other 4. So we're going to have to take those 6,840 and multiply them by the 2,380. So here, this is kind of like where we're using the fundamental counting principle. So altogether then, we get 16,279,200 different ways that we could form this committee. And again, if you had this problem on a quiz or a test, remember you'd want to write your answer as a complete sentence. So you would say there are 16,279 or 279,200 ways that we could form this committee. Okay, so that's a really good example because it's showing all three concepts that we've been working with. It's got the permutations, the combinations, and the fundamental counting principle all together. So that's a very good problem. And those are the higher level problems that we need to be working with now that we're in pre-calculus. So you don't get too much exposure to probability and statistics in your other math courses. You just get a little bit of it. So now we've got to take that little bit that we do know and put it all together into these bigger, higher level thinking problems. So again, make sure that you go through these problems, these homework problems, and ask yourself, does order matter? Does it not matter? Can I just select different items and use the fundamental counting principle? So go through that thought process, and that will help you decide what type of a problem you're dealing with. But check the odd answers in the back of the book, and then solutions are worked out on the class website. And if you still get stuck, come on in and see me before school.